Hello everyone, this is Sanabaina Sanjeev Kumar from Aero. Today I am going to tell about array and data structure of algorithm and the data structures for new model of computation. So, in the early days of computer science, the community settled on the simple standard model of computing and a basic canon of general purpose algorithms and data structures. The standard model of computing has one processor that performs a single instruction at a time, copious memory that is uniformly accessible with a negligence latency, readily available persistent storage with significant latency, input and output that is insensitive to content or context, and orders of magnitude slower. Resources and connections that do not change, and if no significant concerns about energy use or component failure, permanent or intermittent. Programmers will not be prepared for modern systems with only this background. Although hardware caching and system support well approximate the standard model, developers must be aware of constraints and idiosyncrasies of a software execution environment. New constraints of time, space, energy, and hardware motivates new ways of thinking and lead programmers to need new approaches to old problems. So many advances have been made in hardware and systems that slavishly staying within the standard model forgoes much performance. Example algorithms and data structures of the given topic is in this section we give four instances of elegant, generally useful algorithms and data structures that were developed for particular circumstances but are not widely known. They illustrate the opportunity to create new algorithm and data structures motivated by new computing constraints. Reservoir sampling for the first algorithm consider a stream environment that is in turn items arrive one at a time. The program does not know how many items will arrive, or equivalently an answer may be required of an unspecified number of items have arrived. As we can see, the index of an memory allocation will be given with an address of 200 and with the starting index of 0 to and so on. If you are giving an input with a UBFDAEC, then the first element is considered as 0 index and the last is considered as nth element. In that, the address is given like 200, 201 and so on. So as we can see here, it is the binary search tree data structure. From that, as we can see that they will modify the nodes and soft side where that heads and nodes on right side higher than the most. So as we can see, the nodes will be increased in right side and the nodes will be reduced in left side. As you can see, the 100 is divided into two parts with a 50 and 150, so that the increment of a 50 over right side and decrement of 50 over left side is given, so that the nodes will be higher on right side. The challenge is to choose one of the items randomly with all items having an equal chance of being chosen. If the number of items is known beforehand, one could generate a random number in the range of the number of items. Alternately, one can store all the items possibly in some data structures that can grow as needed and choose one when needed. A simple solution is attributed to Alan G. Waterman. It requires storing the item chosen so far and then counter and the holds the number of items from the stream so far. Wishkin gives a parallel algorithm to compact an array in a theta log n. This is a big O notation, O log n and theta log n. The assuming time complexity of a theta n hardware. The input is the shared array A of size n. The output is shared array B assumed to be big enough. To help explain the algorithm, we present the XMTC code for it as reference. As you can see, it's a C program code with a spawn of 0 to n minus 1 and the int is equal to 1, so that if astra is not equal to 0, ps is e into dash p of e. As you can see, it is a tree structure. In this binary tree data structure, the single element will be divided into so many subparts until we get a single element. It's more likely to be said as a merge sort. So finally, when we get a single element, it will be sorted in this data structure. And as you can see here, 1 2 3, as you can see, the first element is divided into 2 and 3, and so that 2 is divided into 4 and 5, and the 3 is divided into 6 and 7. As you can see in this previous case, it is in theta of log n and with a time complexity, and assuming that it is a theta n in hardware, so the time complexity will be increased and more likely to be it will be taking more time than an expected time. So the time complexity of this program will be more likely increased within the time, so that we use this XMTC code to run it and to make it in an easy way. As here it is said that in this binary data tree structure, the single element will be accessed individually. As you can see, the 8 is divided into 4 and 10, then that 4 is divided into 2 and 3. The 2 can be divided into 1 and 3, so that 1 minus 3 will get 3 minus 1, or 1 minus 3 will get a positive or negative 2. More likely from 6 we got 5 and 7, and more likely from 10 we get 9 and 13. Then 13 is divided into 12 and 15, and the 12 is divided into 11 and 14. So as we can see, the single element is divided into number of elements with a time complexity taking more, and we get a last single elements for each program. And as you can see in this big tree structure, that 1 is divided into 47. The final single element we got is the 47, which is very muchly like to increasing it. So this is all about the binary tree data structure. Thank you.